Greetings and welcome everybody to Chapter 2, Lesson 2-4, Solving Equations with the Variable on Each Side. So today's learning targets are as follows. We will solve equations with the variable on each side. We will also solve equations involving grouping symbols. So how will you know that you have successfully learned these learning targets? Well, you will be able, at the end of this thing, to solve and prove equations with one or more variables on each side of the equation. One or more variables. Also, you will be able to solve and prove equations with one or more grouping symbols on both sides of the equations. So we are building up our foundational equation solving knowledge. We're starting to get into things that are a little bit more complex and complicated, and it's going to serve us some very valuable purposes later on through our Algebra 1 journey. So let us consider the journey today, though, and keep these key questions in mind as they will guide us on that journey. So, what operations are needed to isolate the variable on one side of the equation is something to consider. When does an equation have no solution? What, when is an equation true for all values of the variable? What is the first step to solving an equation with the variable on each side? These questions are quite important, so keep them in mind as we go through, for their answers will be revealed here shortly. So let us let us just dive right into this thing, guys. So I've set up a little scenario here, but before we get into the scenario, I want to say that oftentimes you will in life encounter these problems, these oh, similar, there we go, similar or related problems about a specific variable in question. Right? The variable can be anything. It can be anything really. And through my little scenario here, we're going to talk about a specific variable and see how two separate problems can be related. And when they are related, we can solve and come to some understanding about what's going on in a real world context, in a mathematical sense, and beyond. So, let us assume that you are in a race with your friend, just a running race, right? Your friend is slow, in fact, So, in the interest of fairness, you agree to give your friend a 500-foot head start. A 500-foot head start, let's say. So let's say this here is your friend. So, let's see. With that said, you being the fast friend, you are faster, and you decide, you know what, I'm going to start at the start line, right? You know, give him a chance, give you the chance, right? See indeed if you are truly as fast as you believe you to be. Okay, all right, not a problem at all. Now, because you are faster, it should be fairly intuitive to you that eventually you're going to pass him up. Your running speed is 25 miles an hour. His is 15 miles an hour. You guys will eventually pass each other up because there is such a significant difference in your speeds. And so, and so, the question becomes, after some time, you both will be the exact same distance away from the starting point. As I said, this idea that you will pass up your friend here. So the question we need to understand is when? When will we pass him up, our friend? When will we pass him up? That is an interesting question to consider. Let's consider let's consider that a little bit more thoroughly. Well, let's see. What was the specific variable in question? Well, when. The question that I had highlighted there, underlined, bolded, all these things, the specific variable in question was time, the variable of time, and I'm going to represent that as t. Generally, you'll see that in all sorts of math and physics and all these different applications. T is time. So in that scenario, listen, it was beautiful artistry, by the way. Bravo to the artist. With that said, it was also real world context. And math is real world. It's just, it is numbers and letters on a board and so forth, and it is that, but it's not just that. It models real life. And so we can create an equation to model real life. In fact, here is that equation that models that real life scenario. We have, let's see, this might be your friend or you. I'm not quite sure here. Let's figure that out here in a second. We have these two different things here. So if I look at each component, each element, each term of this model, this model of our real life scenario, 25t. Well, if I think about it, 25t, from the problem, you can remember, think about that's 25t was the speed of the fast friend, which in this case happens to be you. So this was here your speed, right? Your speed, 25 miles per hour at a point in time, the point in time being the variable itself at a point in time. Okay, so if that 25t is true, that it's your speed, well then it makes sense that this zero here is where you started from. It's where you started from. In fact, it is your starting position, your starting uh, position. Basically, you had your yeah, I'll just call it starting position. That's fine. Starting position or starting time or time. Okay, great, 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 great. So let's see here. If that's true, this then is you. Then this here is your friend. It must be your friend. And let's see. Let's see here. Okay, wonderful, wonderful. So let's see. If that's your friend, and he was the slower one, this 15 here should be your friend's speed. Your friend's speed at a point in time. Okay, that makes sense. And then this 500, well, that 500 represents the head start that your friend was given. The head start position of your friend. Okay, that's perfect. Let's see. Does that make sense though in our scenario here? Let's go back here and look at it one more time. Let's see. 500 foot head start. This actually should be not foot, but 500 second head start. Let's see. Anyways, let's see. Your friend is slow. This little picture here certainly seems to model See, it certainly seems to model the scenario in question here. Okay, perfect. So let's see, what is our goal here? Let's keep our goal in mind as we take this real life scenario, this word problem, build a mathematical model from it. What is the goal though? It is simply to answer the question that was posed to us. When will they pass each other up? So in other words, our t has to equal something. We don't know what right now. That's what we will find out here soon enough. But our t has to equal something, right? T equals something, variable equals something. That's sort of our whole goal in equation solving is to isolate, to get it by itself, and everything else on the other side. That's sort of the goal. Okay, no problem here. So keep that in mind, though. Keep that in mind. So to achieve this goal, we must combine like terms. Now, we've combined like terms before when we've had equations that sort of resemble perhaps this, we've had equations like this where we've had to combine like terms, and this would have been, we would have combined this, and this would have been 7x equals 15. We've combined terms like that before, and that isn't necessarily new to you at this point, but what is new to you at this point is the idea that we are going to combine like terms by performing our favorite term, our favorite phrase here, by performing inverse operations. Now again, before I have to highlight this because this is how important that this term is to mathematics and to us specifically and so forth. So inverse operations, if you've stuck with me now for a couple videos, you will know that I have referred to this as simply being do the opposite. Do the opposite. So for example, if we see a plus 2, opposite of that, minus 2, and so forth and so on. Not going to harp on it too much, but understand that's why it's our favorite phrase. We do so all in the name of balance, and et cetera. But anyways, let's see. So we do the inverse operations to eliminate terms from one side of the equation to transfer them to the other side. All in the name, like I said, of balance, right? We are in compliance with mathematical law. We are in compliance with the fundamentals of mathematics and the properties of mathematics and so forth and so on. Okay, so let's consider solving this here. All right, so here's our model. I want to answer the question, when will the two runners, you and your friend, meet each other on the field, pass each other up? When will that be exactly? Well, let's see. I gotta start performing inverse operations with the goal of getting all the t's onto one side and everything else onto the other. So let's do that. Let's get this. So I see a t here and I see a t here. I notice first and foremost, they are on opposite, or they are on opposing sides. They are on, they're not all on the same side. So I want to get them there. So let's do that. Minus 15t, if I minus 15t from both sides. Now, let me just interject here for a second and say that I like to gather up all of my variables onto the left side of my equation. Now, that's just my personal preference. You don't have to gather them all up on the left side. I tend to do so unless I have a very specific reason not to. It's just how I like to look at things. The way I read things is x equals whatever, or t equals whatever, or so that's just again, you don't have to. You could get it all on the right. It's fine. You just got to deal with negatives. That's fine. Nothing scary about negatives. Anyways, so let's see here. 25t minus 15t equals 10t. Let's see, plus 0. I don't really have to worry about the 0, so that's nice. And then 500. 500. Okay, nice, nice, nice. Let's see. Okay, and if I divide 10, I undo that multiplication, divide 10, t equals 50. Now I'm gonna, so this is what it's saying. It's saying t equals 50. Time equals 50. Now I'm gonna say that we're talking seconds here. So seconds. Time equals 50 seconds. So at 50 seconds into the race, we will indeed have a situation in which you pass your friend up. Okay, excellent. So let's do this thing. Let's prove this out here. So I'm going to put 50 over here. I'm going to put 50 over here. Substitute. We prove things. We do so because we don't just accept things at face value. We prove things because the whole idea behind equations is to create statements of truth. Get something equals that exact same something. When we form statements of truth, we know equations are in balance. That is the fundamentals of mathematics right there. So with that said, 25 times 50, that simply becomes 1250. Yep, 1250 indeed. So 1250 equals let's see, 15, let's see, times 50, that becomes 750 plus 500. Okay, I got some stuff here to simplify and combine. Let's see, I got 1250 equals 1250. Okay, so first things first, this is true, guys. This is true. Secondly, let's think about a few things here. So we always start by solving and then proving, okay? But when we solved, let's see, what is exactly it saying that we're solving? It gets us a a factor of time. Well, I kind of already spoiled it, I guess here. It gives us a factor of time at which when the two runners meet, two runners meet. Now, with that said, though, generally we prove things, just for the sake of being correct, but here in this real world context, this scenario that we've built out, there's actually information gathered from the idea of proving it out, information that we didn't have before. So the information we didn't have before, and the reason why it's so critical to prove things out, here's another example, is that from doing so, we ended up ascertaining the distance, the distance where they met on the field, the distance when they ran, at which point they passed each other up. And actually, real quick, now that I think about it, I don't know why I crossed these out, uh, but yeah, it should be in terms of feet. And I don't know why I did that. Yeah, feet. That makes sense. Okay, so yes. Anyways, there we go, guys. There we go. This we sort of fairly quick into our journey here. We've sort of taken a real world scenario, decomposed it into its mathematical elements, and then manipulated the mathematical elements to get us important information, such as the time when the two runners met on the field, such as the distance where they met on the field, the distance into their race where they met onto the field. So very quickly, we got a lot of good value out of that. So but, we got to keep practicing, guys. For practice makes perfect. So let's run through a few more basically examples here and we'll see what we encounter. So, notice first, I got a variable here and a variable here. They are separated by an equal sign. That means, again, consistent with the goal here, I want to get variable equals something. I want to equal variable equals stuff. I want to get variable all by itself, isolated, equals all that stuff. So let's do that here. Let's start moving things around by performing inverse operations. Performing inverse operations. Now, if this confuses you, let's see, I'll do one at a time. So in the interest of space, there's not a lot of space here. So basically, I'm going to use this one line. I would traditionally use this and I would get 2 plus 2k equals -6, and then I would go ahead and minus 2 on this other separate line, right? Two lines, or this would have been one of my inverse operation lines. This would have been my other one. I'm just going to combine it all into one line in the interest of space and frankly time. So if it confuses you, that's sort of what I'm doing. So I'm sort of doing all of my inverse operations in one line and then getting a result. So 2 minus 2 happens to be 0. 5 minus 3k happens to be 2k. These cancel and leave us with a 0. Minus 6 minus 2, that's minus 8. Okay, now this looks much better. I got one more step to do. Divide 2, divide 2, k equals -4. Let's prove this, guys. Let's prove this out. Are we right? Well, you never know, really. Could always make a mistake. Let's see here. If I substitute -4, -4, this becomes 2 minus 20 equals minus 12 minus 6. 2 minus 20 is -18. Whoa, okay. Here we go. 18 equals negative 18. Oh, guys, hello. Yes, it is true. Nice. We got a statement of truth out of that. Our outcome, our result was true when we plugged in our input. We substitute our input. Therefore, k being negative 4 is indeed correct, for it resulted in a statement of truth. Excellent, guys. Excellent stuff. All right, let's proceed forward. All right, so we got something else going on here. Let's see here, another one of these. Okay, well, let's see here. Now I remember I specifically said I like to gather all my stuff up on the left, and it's true. I mean, I certainly could do that here, but I'm gonna move this on over to the right. And the reason is I just don't want to work with negatives. That's really what it boils down to here. So I'm not going to. I'm going to if I take away this 3w here like that, and okay, 2 equals 4w, divide 4, divide 4. I get, and this reduces down to 1/2. If you are not familiar with reducing, you know, I'll accept it, I suppose. However, understand that 2/4 is factorable by 2. You can, you know, 2 and a 4, they are both factorable by 2. And and so, right, I know we haven't really covered factoring yet, but fear not, we will. Okay, so if you multiply these across, you get 2 over 4, same thing. They share in common a 2, which would cancel each other out, which leaves us with 1/2. That's sort of the idea behind reducing. Don't worry about it for now too much, right? Just understand that it's a thing. But the important thing here is we have an answer. Now let's prove it. Let's prove our answer. So let's see here. I got my 3, and I have plus 2 equals, let's see, 7, and I got that. Okay, so let's see. I got 1/2, 1/2. Now let's see here. I may have mentioned this before. Well, maybe not. But one thing I notice with students is that when they see this, I'm just going to focus here on this term specifically for the moment here. When they see this, they get slightly confused as to what's going on here. How do you evaluate that? Right? Now, with that said, if I, instead of using 3, I use 3 over 1, they've had fraction. They've worked with rational numbers and did operations such as addition and subtraction, multiplication, and so forth up to this point to get to where we're at in Algebra 1. And so when they see that big 3 represented as a 3 over 1, it sort of immediately clicks to them that, I'll multiply across the tops, multiply across the bottoms, and you get 3 over 2. If this is you, if I'm describing you as a person who got confused when you saw that big 3, I want you to begin to understand that every number you see out there, you can just sort of envision it to be its fractional equivalent, right? When I say fractional equivalent, what I'm saying that indeed 3 is indeed equal to 3 divided by 1, right? When you do this, you do get a 3. This here is the 3 over 1, and we're saying it equals the 3. That is indeed true. That's a true statement. So, like I said, if big 3 over here confused you, start getting in the mindset that every number you see is over 1. Even fractions themselves, right? Even fractions themselves are over 1. We just in math don't tend to write over 1 for reasons, but start thinking that, for it will make your life so much easier going forward. Anyways, let's continue. So this is 3 halves plus 2 equals, again, I'm going to envision this to be a 7 over 1, and then that makes it more clear to me that I have a 7 over 2 situation. Okay, wonderful. Let's see now. Little, I don't want to say problem, but slight recognition here that I'm adding a fraction to a whole number. Can't do that. Can't do that because, once again, envision this as its fractional equivalent. I cannot add fractions with unequal denominators. I must find a common denominator. And luckily, it's not super complex to find that common denominator here in this particular case. In this particular case, that common denominator would be would be a result of multiplying just this term by 1 or another form of 1, which happens to be 2 over 2 is indeed 1. It equals 1. It's another form of 1. So I'm going to multiply it by another form of 1. I can do that mathematically and not have to do it to the other side because anything multiplied by 1 is simply itself. If I multiply something by itself, it does not create an imbalance. Thus, I can get away with doing this in order to find that common denominator. Anyways, I don't want to get super in depth on that, too mathy on you. Just know all I'm doing here, find the common denominator so that I can combine these two elements, these two terms. So let's do that. Let's see, 2 times 2 here is 4. And then 1 times 2 is over 2. And then I had this 3 halves to begin with. And now I have 7 halves. And so let's think about this here for a second. 3 halves plus 4 halves equals 7 halves. Well, 3 plus 4 is 7 halves equals 7 halves. And indeed, that is true. That's true, guys. This, when I substituted 1/2 in for W, it resulted in a statement of truth. Therefore, I know W was correct. Let's look at another. Let's look at another, guys. Let's look at another. Okay, so again, this whole idea is that we're going to have variables on opposing sides of the equation. But we can deal with that. And in fact, let's do that now. So I got plus 7a. Doing so is the inverse. Doing so eliminates it. That's what I want. I want to eliminate these things. And of course, consistent with what I said earlier, I'm going to do these all on one line in the interest of space and time. So let's see. 12a equals, let's see, that becomes 0. That becomes 6 minus 2 is 4. And then minus 7a plus 7a, that becomes 0. So now I'm left with this. 12a equals 4. Divide 12. Divide 12. I am now left with a equals 4 over 12. Or if I reduce, right, there's a common factor of 4 between these two items here. And if I reduce, that simply leaves these 4's to cancel, and I'm left with 1/3. So a is in fact, well, I'm saying a is 1/3. Is that true though? Well, let's prove it, guys. We must prove. We must prove everything we state here. For if we get an error, well, we don't want to have an error. And that is the goal of mathematics is to have statements of truth. All right. Anyways, so let's do that. So 5 times 1/3 plus 2 equals 6 minus 7 and 1/3 there. Okay, great. Again, if this helps you out, I'm going to get rid of big 5 and put its fractional equivalent. I'm going to get rid of big 7 and put its fractional equivalent. Therefore, it's more recognizable to me that I must perform a multiplication here. Cross the tops, cross the bottoms. I end up with 5/3 plus 2 equals 6. Multiply the tops, multiply the bottoms. I get a minus 7/3. Okay, not bad at all, not bad at all. So what do I have to do now? Well, I have to recognize that I got fractions and I got whole numbers. In fact, I have that on both sides. So I must get these to have a similar, or not similar, but exactly the same denominator as the other one so that I can sort of combine stuff. So you saw I erased big 2 and big 6 and I replaced them with their fractional equivalents. That stands out to me more as a need to get common denominators, and so I will do so. And in order to do so for this one here, I have to see if I have space here. I have to multiply by a form of 1, and that particular form of 1 happens to be 3 over 3. And let's see, I'm gonna make some more space here. And if I do the same here, I want to get it to be a 3 so that it can combine over here. Again, I must multiply it by a form of 1. Okay, nice. So let's do that. Let's see here. I got 5 thirds plus 6 thirds equals, let's see, that becomes 18 thirds. And this becomes, oh, this is just simply 7 thirds. So let's see, I got everything in terms of thirds. That's great. Now, let's see, I'm going to put this over here for the time being. Put this over here for the time being. Let's see, 5 plus 6 thirds equals 11 thirds, and 18 minus 7 thirds, or 18 thirds minus 7 thirds, happens to also be 11 thirds. Hey guys, these two things, this and this, they match. Therefore, it's true. True. We got a true statement here, guys. That way, that means we're saying that this 1/3 we got earlier, we're saying A was 1/3. That's true. That is correct because we ended up with a statement of truth after we substituted it in our proving phase. Okay, let's look at this here. This one. Whoops, hold up a second here. There we go. Nice. Okay, so this one's a little bit more complicated. Now, I want to point out here before I really get going here, you will oftentimes see fractions that look like this. Now, this may potentially confuse you. In fact, I know it confuses students. So I just want to point out that really when you see variable over, something, what it means really is just this x over 2. You can just envision this to be 1/2 x, 1 over 2. For you see, if you were to take 1/2 times x over 1, multiply the tops, the bottoms, you would get x over 2. That is, that just is reality. Again, in math, we like to simplify things. We like to maybe be lazy, some may call it. Either way, we tend to sort of ignore anything divided by 1, anything multiplied by 1. So don't get confused when you see x over 2. It just means 1/2 of x. So instead of doing that x over 2, I'm going to represent it from this point as 1/2 x. Hopefully that makes things a little bit more clear for you as we begin to solve these. So I'm going to go ahead and start performing inverse operations. Now this may look maybe funny to you. I'm subtracting a whole fraction. Yeah, that's okay. You can do that. There's nothing wrong with that. In fact, that is exactly what you must do at this point. You must get this x over here, right, over there. Or, you can take this one and move it over there, whichever one. But ideally, yeah, you are subtracting a fraction, and, you must. So there's that. Again, if I'm going to move everything to the left, that appears to be the case what I'm doing, I'm going to go ahead and get rid of this 1 and get rid of this and there. Do everything in one line. Okay, so now I'm left with 1/2 x minus 1/4 x equals -7. Okay, so let's see, I got a 1/2 x minus 1/4 x. What I need to do is get a common denominator. So that's what I'm going to do. I'm going to get a common denominator here. I can do 1/2 x, and I can multiply this by another form of 1. So another form of 1 happens to be that. And this all remains the same. This all remains the same. So let's see if I do that. I get 2 over 4. 2 over 4 minus 1 over 4 equals -7. Okay, so now these are both common denominators. That means I can proceed. I can proceed. See, 2 over 4 minus 1 over 4. You end up with a positive 1 over 4x equals -7. Now, I wish I could say I was done, but I'm not because I still have x not all by itself. I have x being multiplied by 1/4, so I must divide by 1/4. And when I divide by a fraction, in reality, what I am doing is I am multiplying by its reciprocal. So that's what's going to happen here. I do the same to the bottom part of the fraction, the top of the fraction, and to the other side of the equation itself. So there we go. This all cancels now and just simply becomes 1x over 1, or in other words, simply just plain old x. And then I have here, again, I'm not going to write big 7. I'm going to write its fractional equivalent, so it becomes a little bit more clear that what we're saying here is -7 times 4 is -28 over 1, and then I can go back to big 28 for final answer. Is it final answer though? Well, I won't know until I prove it. So let's do that. So I'm gonna put it in there and I'm gonna plug it in over here. There we go. Let's do this thing. All right. So I can go ahead and put, see, I'll go ahead and put -28, 28 over 2 plus 1 equals 1 over 4 times -28. And I'm going to go ahead and represent that 28 as its fractional equivalent right away, and then -6. Okay, let's see, so -28 over 2 happens to end up being -14 plus 1, and this happens to be multiplied across the tops. Let's see, -28 divided by 4, that happens to be -7, and I have this -6, so I have -14 plus 1, that's -13, and this here becomes -13. Oh, wait a minute, guys. We have some truth happening. For this is exactly this. This is true. Therefore, W, what we determined it to be, -28, the input into our equation that satisfied the equation, resulting in a true statement. Therefore, X is indeed 28. Little bit scary. We're working with fractions. I know fractions are a very scary thing for students, but they aren't so bad, hopefully. I love them. We'll see. We'll see how you feel about them later, right? Anyways, here we go. Let's continue forward. Let's press on. Let's talk about the idea. Remember, we were going to solve equations with variables on each side. Now we're going to do so when they involve grouping symbols. And so, to basically get us going here, there are at times terms, or they're the terms, in fact, and expressions on either side of the equation will be presented to us with grouping symbols. With grouping symbols. And, you may be more familiar with the terms, let's say, parentheses, and even brackets. I've used them before. Okay, so one such equation might look like this, right? It has grouping symbols. It has grouping symbols. So from the above, we must recognize this and this. They are the terms that contain the grouping symbols in this equation. And when we see grouping symbols represented in the way that this is, right, we have a 5 multiplied by grouping symbol, 2 multiplied by grouping symbol. This may trigger some memories as to what we must do. In fact, this may trigger some thoughts as to an opportunity to apply the distributive property, another fundamental mathematical law, a fundamental mathematical property, in order to achieve the result of distributive property in these cases. The result of distributive property in these cases is 5x minus 10 and 2x plus 14, respectively. And so when we recognize that to be the case, we then end up with a result that looks something like this, right? All I did was just distribute at this point, right? Just distribute this, and now this I'll call it the left side of the equation. So I'll call this L, and I'll call this R for right. So now I recognize that left side of the equation has now opportunities for us to simplify a little bit more. It has, in fact, opportunities for us to combine. Actually, both the left and the right, they both have opportunities for us to combine like terms on their particular side of the equation. So combine like terms. We've done this before. We've done it in this lesson here and in previous lessons. So the difference here, though, is that we will ultimately combine like terms on the same side of the equation and then combine like terms through inverse operations like we've been doing. But anyways, let's not get ahead of ourselves here. Let's do let's think about things a little bit. After all the grouping symbols symbols are essentially gone, which is kind of what I elaborated on here. Once they are gone, and all like terms, so like terms being this 4x and this 5x, are combined, the expressions, that's what these are, these halves of the equation, the halves themselves are called expressions. These expressions are what is known as in simplest form. Once they are combined, once the grouping symbols are removed. Okay. Once they are then in simplest form, though, we can then at that point, that is the point at which, in fact, I'm going to highlight that once those expressions are in simplest form, after they are in simplest form, we are then ready to begin performing inverse operations. Inverse operations. In order to achieve our problem-solving goals, which, again, our goal is always to get variable equals stuff or something or whatever, what have you. So let's actually end up solving that little, we've been talking about it. Let's solve that one through to the very end here. Okay, I didn't want to spoil it above here, but here we go. Now it's time to spoil it. Now it's time to solve it. So first thing I must recognize is that I must perform distributive property before I do anything else, because I can't start combining things until I do that. So I want to remove all my grouping symbols by performing distributive property. This becomes 5x. This becomes minus 10. I got 4x here. Let me create more space here. There we go. Okay, equals. Now let's see. I got a 2x, and now I have a 14 minus x. Okay, great. Distributed everything. Now, as I said, so maybe I'll even put right here. You know, we ended up. So we did the distributive property as our step. Perfect. Now, let's see. Let's combine like terms on the side of the equation on their respective sides first. All right, so these combine here. So now I have 9x minus 10, and that equals, let's see, 2 minus 1 is just plain x plus 14. So here I then now did, this is the result of combining, I'll put CLT, combining like terms. Now I can perform inverse operations. And I'm going to collect everything off to the left like I typically do. So I'm going to remove this here with the intent, or I'm going to perform an inverse operation here with the intent of eliminating it from this side and transferring it over to this side. So there we go there. I'm going to perform an inverse operation here with the intent of eliminating this and transferring it over onto this side. Okay, so 9 minus 1x, 9x minus 1x happens to be 8x. Okay, again, this eliminates, and this eliminates, and I have a 24. 14 plus 10, 24. Okay, that right there was inverse operation. Inverse operation right there, and it will also be the case that what I do here will be inverse operation as well. So 8 multiplied by x, to undo that, to inverse that, I must divide, therefore I'm left with x equals 3. Is that correct though? Is that correct? Well, we must prove, guys. We always prove everything we hypothesize. When we solve for a variable, it is simply a hypothesis until we prove it. Okay, so now, okay, all right, now, so recall your knowledge of order of operations. For that will really help you out big time here because I've got a lot of grouping symbols happening here, and I don't want to necessarily mess it up and it results in a crazy solution here. So let's remember order of operations. We start with parentheses, but I see parentheses within parentheses, start with the innermost and work our way out. 3 minus 2, that happens to be 1. Okay, 1, and then I have this, and I'm going to build out. Oh, wait a minute, hold on a second. I forgot to plug in over here too. There we go. I need to plug it in right here too. Any others? Oh, yes, here as well. Tricky. Okay, so let's see here. Okay, then I have 4 times 3 plus that equals, let's see, work in going outward. This becomes 2 times 10, and this is simply 3. Okay, so let's see. Again, order of operations, do multiplication first. So 12 plus 5 equals 20 minus 3. Okay, now I'm at a point now where I can, you know, evaluate these sides here. All I have left is addition and subtraction. 17 equals 17. Hey guys, this here, this thing here that we just did, yeah, 17, 17. Yeah, that's true. That's true. Our input of 3 resulted in a statement of truth. Thus, our input is correct. Excellent, guys. Excellent work. Excellent job here. Let's roll through some more, though, for we are not done. We must sharpen our knowledge, sharpen our skills, and become super duper proficient at this stuff, for we will see much, much more of it in the coming days and weeks and months ahead. First thing here, guys, distribute, 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 and distribute. This leaves me with 30m. This leaves me with 18 equals, let's see, 1/3 times 24 is 24 over 3m. However, I'm going to, in the interest of space, I'm going to simplify this to be what it is, and what it is 8m. Okay, and then similarly, I would get 12 over 3 if I distribute that properly. But in the interest of space, I'm going to represent it as 4, because that's what it would come out to be, right? 12 divided by 3 is 4. Now let's see here. Okay, I'm going to start collecting things off to the left. And I'm going to start inversing this, and I'm going to inverse this. All right, let's see. So now I have 22m, and this becomes 0, and this becomes 0, and then this becomes 22. Huh, interesting here. Interesting. I'm going to inverse the multiplication of 22 by dividing it by 22. M now equals simply just 1. Interesting, interesting. Okay. Prove to me it's 1, you say. Prove, and prove I shall. Prove I shall. So, 1, 1 goes there. All right. So, PEMDAS, order of operations, work in, then proceed outward. 5 times 1, that's 5, minus 3, and that equals, let's see, 24 plus 1, or times 1, it's just plain old 24, plus 12, so 24 plus 12, 1/3 of that. Okay, let's see, this has become 6 times 2. This becomes 1/3 of 36. So this becomes 12. And 36 over 3, that becomes 12. So 12 equals 12. And that's true, guys. Bam. We are rocking and rolling here. We're rolling through. We're moving on, and we're getting this. I'm so glad that you are getting this. Let's try some more. All right. Let's see. I see one opportunity for distributive property to be applied. Let's go ahead and do that. Let's see here. 18 minus, let's see, 3 times minus 2s happens to be minus 6s. Okay, and then I have 8s minus 10. Now, let's see, I'm going to collect everything off to the left, as I typically do, as I typically do. Again, these are s's, not 5s. If you, I know my handwriting's not the best, but I just want to point that out. So 18 plus 6s, or sorry, 8s plus 6s is 14s. This eliminates. 18 plus 10, that's 28. And these eliminate. So now all we're left with is a 14 times s. I want to undo that via division, and s now equals some stuff, and that stuff happens to be 2. Prove it. Prove it, prove it, prove it. All right, so I have 8s minus 10. Oh wait, oh sorry, I gotta put my 2 there as well. Okay, minus 10 equals 3 times 6 minus, let's see, 2 times 2 is 4. I'll just go ahead and do that there. Okay, nice. So let's see, 8 times 2, that's 16 minus 10. Okay, and then I have here 6 minus 4, that's 2, and then 3. So I have here, let's see, 16 minus 10 is 6. And I have here 6. And guess what, guys? 6 does equal 6. True. Next one. Next one here, guys. Okay, so I have opportunities to distribute. 2 opportunities to do so. 1, 2. All right, distribute, distribute. Okay, 7n minus 7 equals, let's see, minus 6 and minus 2n. Okay, collect to the left by performing inverse operations. Collect these non-variables off to the right by performing inverse operations. Okay, let's see, 7n plus 2n equals 9n. This becomes a 0. Minus 6 plus 7, that becomes a 1. And this becomes a 0. So now I have 9 multiplied by n. Divide 9, n equals 1/9. Phenomenal. Well, is it phenomenal? I don't know. I won't know if it's really phenomenal, guys, until we prove it. Let's see. Here we go. Oh wait, that doesn't go there. That's just a trick. That's meant to trick you guys. in case you weren't paying attention. Okay, so 1/9 would go there. Let's see, 3 goes here because look at the original equation. That's a 3. Meant to, meant to catch you off your game here, guys. And then this would be 1/9. All right, so let's see here. So I'll just kind of cross it out and put 1/9 right there. Nice. Okay, so let's see here. 1/9. Oh, -1. Oh man, we got this reads to me as we got some fraction work to do because I'm taking a fraction and subtracting a whole number. Well, if I multiply this -1 by a form of 1 that gets me a denominator that is the same as this one, that form of 1 would happen to be 9/9. So this may get a little messy, guys. I don't know. Let's keep going with this though. Let's see. I got 3 plus 1/9 here. Now again, same as the other side here. I want to multiply by a form of 1 that gets me this same denominator. So I must multiply by the form of 1 that is 9/9. Okay, so let's see. 1/9 minus 9/9 happens to be -8/9. And that is being multiplied by 7. And instead of big 7, I'm going to write its fractional equivalent, 7/1. Okay, this here equals, let's see, I won't do, oh, wait a minute. Okay, yeah, let's see. I'm going to do, this becomes -2 times, I won't do big 3, I will do its fractional equivalent, so it's a little bit more clear. And I should have said the same thing here, 1/1. That's its fractional equivalent. Either way. Okay, so this would become 27/9, and this would become 1/9. That actually, we didn't do anything to that one. So let's see. Okay, great. And instead of -2, negative big 2, I'm going to do -2/1. All right. So 7 times -8 is -56/9. Okay. All right. That doesn't appear to be divisible by 9, so that's my final value on this side. Okay, now I can just focus my efforts on this side. Let's see, 27/9 plus 1/9, that is 28/9. And I am multiplying that by -2/1, and that becomes -56/9. This becomes -56/9. Hey guys, this happens to be true. Therefore, this 1/9 was indeed correct, for it being substituted back into the equation is what satisfied the equation to be a statement of truth. Not so bad, guys. I know fractions are a little scary, but they are very much doable. So, with that said, let's talk about a couple of special cases that you're going to run into. You're going to run into some sort of special cases and with these ones, and I want you to be aware of them because they may throw you for a loop if if you've never seen it before. So, let's talk about it. Sometimes you will encounter problems in which the variable has no effect. I'm sorry, wait a minute. I'm sorry. Whoops, my bad. I kind of spoiled it a little bit. But what I'm trying to say is sometimes you'll encounter problems in which the value of the variable has no effect on the outcome. Sometimes that will be the case. For example, let's think about real world, for example. In the real world, sometimes, let's see, sometimes no matter how many times you press the power button on your television, no matter how many times you do it. Sometimes it just will not turn on on if it is unplugged from the wall. Well, that should make sense. You know, TVs run on electricity. If it's not receiving electricity, it won't turn on. So if your variable is the number of button presses that you are pressing the remote, it matters not how many presses you do. In fact, there will be no solution to such a problem in which you are asked to determine the number of button presses needed to turn on the TV. There will be no solution because there's no electricity. So it doesn't matter. You could press it once or a billion times. It will not matter. And we can model that mathematically, and you will see equations modeled, or you will see scenarios, you will see equations that model scenarios in which the variable has no effect. There is no solution. And in fact, in such models and in such equations, you will get something like -2 equals 4. That's not a true statement. I mean, an equation is a true statement, a statement of truth. There is nothing true about the idea that -2 equals 4. It just isn't true. And that's when your indication on these sorts of problems that you will get no solution to the variable will make that a true statement. Anyways, similarly, there are situations in life out there where no matter, for example, how much, let's say, money you make at your job, the amount of money you have in your savings account will neither increase or decrease if you spend every dollar you make. So if you spend every dollar you make, whatever's there originally, will still remain there. Thus, all real numbers regarding the amount of money you make at your job. You could make minimum wage, you could make $1 billion at your job. It doesn't matter because if you spend every dollar you make, the value of your savings account will not fluctuate. It will be the same as it was always. And so you will see equations and scenarios modeled where every variable you input will be canceled out and result in equations that end up looking like this without needing to do any variable work. Right? You'll see here in these next few examples what I'm talking about. Anyways, let's look at these next few examples to understand what it is that I'm talking about. Let's see here. There we go. So here is one such situation. First, let us distribute. Do so, I get equals 15x minus 12 minus 10x. Okay, I get 5x plus 5. Let's see that. Okay, great. Now I can combine like terms on the side that it's on, and I'll do that here. 5x minus 12 equals 5x minus or plus 5. Okay, so far so good. I'm just following the steps that I've become accustomed to and familiar with throughout this lesson. So now I want to collect everything to the left or even the right. It really doesn't matter. I'm just going to do what I normally do on the left. So I'm going to inverse that 5x. I'm going to inverse it here. I'm going to move this. I'm going to move this, and move that, right? But here's the thing here. This 5x minus 5x, that becomes 0. Plus 5 minus 5, that becomes 0. Equals, this becomes 0. But this here becomes minus 17. There is no way that 0 equals -17. That is not a true statement. That's not a statement of truth. There is no truth to that. Thus, there is no solution. Solution to the variable which would make this statement true. For if I were to have x be, let's say, 2, right, this would become 10. This would also become 10. I would end up doing 10 minus 10. And I would still get 0 equals negative 17. No matter what the variable would end up being, I could sit here all day until, until forever, and there would be no solution to the variable, which makes the statement that 0 equals negative 17 true. You'll run into that. There's no need to prove it. I like to prove things. There's no need to prove it though. The proof, it sort of broke, you prove what you solve for your variable. We didn't solve for our variable. The variables canceled out. Therefore, there is no proof to do. And so I'm not doing a proof. This, in fact, is the proof. Let's see, let's look at this one here. Let's look at this one here. So distribute, distribute 6b minus 3 minus 7 equals 6b minus 10. Okay, fantastic. All right, that should be a b. There you go. Okay, fantastic. So let's see. Okay, I'm looking. Can I combine my terms first of all? Yes, I can. On this side, I can combine these two non-variable terms. So let's do that. I have 6b now. I have a minus 10 equals 6b minus 10. Okay. Now let's see. If I want to, again, I'm trying to solve for b here. So I'm going to collect everything off to the left like I typically like to do. And in doing so, I can, move this over, inverse that, inverse that. And so what I end up with is 6b minus 6b. That becomes 0. This here becomes 0. This becomes 0. And this becomes 0. Hey guys, did you know that, did you happen to know that 0 equals 0? That is a true statement, guys. Thus, we can say that no matter what this variable is, it will always result in a true statement, and thus all real numbers, any number, every number, all numbers can be substituted in for b, and it still results in 0 equals 0. So you can also say infinite solutions. Infinite. Let's try a couple more, guys. Try a couple more. Let's try this one here. So let's see. Distribute 7x plus 5x minus 5 equals minus 5 plus 12x. Okay. Do I have opportunities to combine here? Let's see. Not on this side, but do I have it on this side? I do. Combine these two. So I get 12x minus 5 equals minus 5 plus 12x. Okay, if I subtract that, I'm going to move it over to the left, subtract that, and then I'm going to inverse this and inverse this. What I'm going to end up with is this is a 0 plus 0 equals, this is also a 0, and this is a 0. Hey guys, 0 equals 0. It's true. Thus, we have a situation in which all real numbers would satisfy this equation for the unknown variable. Whoops, skipped a little too far. Okay, there we go. So we also have this other one to check out here. Boom, boom, distribute, 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 distribute. Okay, so 6y minus 30 equals 20 plus 6y. Okay, let's start moving things over. 9 is 6y minus 6y plus 30 plus 30. Okay, all right, so this becomes 0. This becomes 0. This becomes 50. And this becomes 0. 50 does not equal 0. There is absolutely no solution to the variable in this equation, which would make 0 equal 50. None whatsoever. So let us connect our newfound knowledge with some geometric applications. For you see, math isn't just numbers and letters on the board. It has all connections. It connects to all things in life and the universe and beyond. And geometry is as much as part of real life as runners in a race, which we talked about earlier. Geometry is just as much a part of life. So let us connect our knowledge to geometry. Nothing super in depth, just a quick couple examples here, and we should be fairly well versed at that point in solving equations with variables on both sides and ones with grouping symbols. So let's see. Find the value of x so the figures have the same area. Well, remember, saying area means, you know, basically this multiplied by this, the sides multiplying together. That's what area means. Side times side, side times side. That's what area means. So kind of get that sense initially, for one. And secondly, knowing that, I can say, let's see, find the value of x so that the figures have the same area. So what we're saying is the area over here is going to equal the area over here. So what I can sort of model by that is say that 10 times x, right? That's area. 10 times x, that's the area of just this one side, is equal to the area of this side. So it would be 6 times, and let's see, it would be, this whole side is 3 and x. 3 and x, or 3 plus x. So 3 plus x. Okay, so 10x equals, let's see, if I distribute this, whoa, let's a little more cleaner handwriting here. All right, there we go. 18, let's see, plus 6x. Okay, I'm going to subtract, I'm going to inverse this, I'm going to inverse this. Whoa, hold on now. There we go. Okay, if I inverse that, I'm left with a 4x equals 18, and then I divide, I inverse that multiplication of 4, I inverse that, and I end up with, let's see, let's erase that. I end up with, let's see, 9, I'm going to factor, let's see, they both share a factor of 2, and if I do that, I cancel, I get 9 over 2. Okay, that sounds interesting. I have a number here. Does that number make sense though? Let's see here. Does that number make sense? Well, let's plug it in and find out. So I have 10, as I said, 9 halves equals 6, 3 plus 9 halves. Okay, well, let's see here. Instead of writing 10, I'm going to represent its fractional equivalence because I recognize I'm working with fractions. So 10 over 1. Same thing here. I'm going to represent fractional equivalence and fractional equivalence just for clarity. Okay, so 10 times 9 over 2. Let's see, that would be 90 over 2 equals something. I'm going to focus on this side for a second. 90 divided 2 is 45. Okay, I have nothing further to do on this side. So I'm going to ignore it for now and work on this one. 3 over 1 plus 9 over 2. I need to get a common denominator. How I do that is I must multiply it by a form of 1. In this case, that form of 1 happens to be 2 over 2. For if I do that, I end up with a 6 over 2 plus 9 over 2. These denominators are in common with one another. Thus, I can combine them to further perform operations that would allow me to simplify and evaluate. So 6 over 2 plus 9 over 2 equals 15 over 2. Okay, and then I have that 6 over 1. Multiply the 6 over 1. 6 times 15 happens to be, what does that happen to be? It happens to be 90, in fact. And then 1 times 2 is over 2. Okay, and then I have grand finale here. 45 equals 45. Guys, this is, without a shadow of a doubt, true. 45 is true. 45 equals 45, that's true. So therefore, x is indeed 9 halves. And another geometric application. The difference, though, of course, is that we're not talking about area this time. I want you to be very cognizant of the words and the specific problem what it's asking. It's not asking for area, it's asking for perimeter. Perimeter happens to be when you take all the sides and you add them up. Okay, so this side is actually a 6, this is x, this is 2x plus 2, and this is x. You just add them all up. And it's saying that find the value of x so that the figures have the same perimeter. So again, it's going to be a situation where the perimeter, p, equals p. So let's set up our model. Let's set up an equation to model that. So if I have, let's see, if I have x plus 6 plus 6 equals 2x plus 2 plus 2x plus 2 plus x plus x. Okay, that's what it's saying. So now let's combine like terms on one side, on each side separately, before we start combining via inverse. So I can combine these two here, and I can combine these two here, and I would get 2x plus 12, and I would get this here and this here and these. That would lead me to, let's see, 4x, let's see, 5, 6x, and then I have this, and that's it. So plus 4. Okay, phenomenal. Let's minus the 6x. I like to, again, get my stuff on the left side. So inverse that, 6x, inverse it, and then inverse this, inverse this. So I end up here with negative 4x. I got a 0 here. I got a 0 here. And I got 4 minus 12. That's a negative 8. So if I divide and divide, there you go. This becomes just simply a positive x, positive 1x, over positive 2. Is that correct though, guys? I don't know. Let's prove it. Let's prove us out here. Now, let's see. To prove us out, I'm not going to rewrite this whole giant thing here. You know, I know that that whole giant thing became the shorter version of this, so I'm actually going to plug it into this shorter version here when I do my proof, right? I mean, I can go up here, but why? It's just a lot. Anyway, so 2x plus 12 equals 6x plus 4. So I'm going to plug in my 2 here. 2, 2, see 4. This becomes a 4 plus 12. This becomes a 12 plus 4. This becomes a 16. And this becomes a 16. Hey guys, this is true. Once again, we have a true statement given a certain input. So, whoo boys, guys, this was a lot to take in all in one day. There was a lot to cover. Again, we are building up toward working with more and more and more complex equations, and we're getting into some complex territory, I must say. But we were able to do it, we were able to persevere, and we were able to accomplish our objectives, which once again, we set out to solve equations with the variable on each side, and we also set out to solve equations involving grouping symbols, and we were successful in doing so. We solved equations and proved equations with not just one variable, multiple variables. In fact, this last geometric one, we had 3 variables, or actually 1, 2, 3, 4 on one side. Crazy stuff. Anyways, I hope you enjoyed the lesson. I hope you got some value out of it, and I will see you next time. Have a good day. Take care. Bye bye.